A two-variable Karnaugh map K-map is a tiny 2x2 grid that helps us see patterns in a truth table for variables A and B. Imagine a 2x2 checkerboard where the rows represent A and the columns represent B. We use gray code ordering so that adjacent cells differ by only one variable. The row labels are 0A equals 0 and 1A equals 1. The column labels are 0B equals 0 and 1B equals 1. The four cells are then identified by the minterm numbers. 0, 0 goes to M0, 0, 1 goes to M1, 1, 0 goes to M2, 1, 1 goes to M3. To construct the map, draw the grid, write the row and column headings, and place the output 1, 0 or X for don't care of the truth table into the cell, whose coordinates match the input combination. The result is a visual snapshot of the function f of AB equals sigma m. This simple visual layout is the foundation for grouping and simplification. Once the two-variable map is filled, we look for groups of ones that can be combined. A group must be a rectangle containing 1, 2, or 4 cells and must be a power of 2. Each group represents a product term implicant that is true for all cells inside it. A prime implicant is a group that cannot be enlarged without including a 0. An essential prime implicant is a prime implicant that covers at least one minterm not covered by any other prime implicant. Example: suppose f of a comma b equals sigma m of 0, 1, 2. The map shows ones in cells m0 open parenthesis 0, 0 close parenthesis, m1 open parenthesis 0, 1 close parenthesis, and m2 open parenthesis 1, 0 close parenthesis. We can form a group of two cells covering m0 and m1 they share equals 0, so the term is a prime. Another group of two cells covering m0 and m2 they share b equals 0, giving b prime. Both groups are prime because they cannot be made larger. The minterm m0 is covered by both groups, but m1 is covered only by the first group and m2 only by the second. Hence, both groups are essential prime implicants, and the minimal SOP is a prime plus b prime. Three-variable K-map expands the idea to an 8-cell layout, usually drawn as a 2x4 rectangle. The variables are split: two variables, say A and B, label the rows, and the third variable C labels the columns, or vice versa. The key is to keep gray code ordering for each axis, meaning adjacent columns differ by only one bit of C and adjacent rows differ by only one bit of A or B. One common arrangement uses a B as a combined row label 0, 0, 0, 1, 1, 1, 1, 0, and C as the column label 0, 1. The cells are then indexed by the 3-bit minterm numbers: the top left cell is 0, 0, 0, M0 next column 0, 0, 1, M1, and so on, wrapping around when the binary count jumps from 0, 1, 1 to 1, 0, 0. This layout ensures that any two adjacent cells differ in exactly one variable, making grouping straightforward. Grouping in a three-variable map follows the same power of 2 rule. Groups can be 1, 2, 4, or 8 cells. Because the map wraps around at the edges, a group can include cells on the far left and far right, or top and bottom, as long as they are adjacent in gray code sense. Example: consider f of a, b, c equals sigma m of 1, 3, 5, 7. Fill the map: rows a b equals 0, 0, 0, 1, 1, 1, 1, 0. Column C equals 0, 1. The ones appear in cells M1, 0, 0, 1, M3, 0, 1, 1, M5, 1, 0, 1, M7, 1, 1, 1. These four cells form two vertical pairs. M1 and M3 share a equals 0, B varies, C equals 1, giving term a prime C, and M5 and M7 share a equals 1, C equals 1, giving term a C. However, we can also make a single group of 4 cells that wraps around the left and right sides. The column C equals 1 contains all 4 ones, so we can group the entire column, yielding the term C. This larger group reduces the expression to the minimal sum of products F equals C. A 4-variable K-map has 16 cells arranged as a 4x4 grid. Variables are split into 2 pairs. The rows are labeled by the first 2 variables A and B in gray code order 0, 0, 0, 1, 1, 1, 1, 0, and the columns by the next 2 variables C and D also in gray code order 0, 0, 0, 1, 1, 1, 1, 0. Each cell corresponds to a unique 4-bit minterm number, from M0, 0, 0, 0, 0 at the top left to M15, 1, 1, 1, 1 at the bottom right, with wrap around on all 4 edges. Indexing can be done by writing the binary representation of the minterm inside each cell, making it easy to locate any combination of a B, C, D. This systematic layout guarantees that any two adjacent cells differ in exactly one variable, which is essential for forming valid groups. Explanation: when simplifying a four-variable function, the goal is to make the biggest possible rectangles, 1, 2, 4, 8, or 16 cells that contain only ones or don't care x's if we choose to use them. Bigger groups give fewer literals in the resulting product term. Example, let f of a, b, c, d equal sigma m of 0, 1, 2, 5, 6, 7, 8, 9, 10, 14. After plotting the ones, we notice a horizontal group of 8 cells covering rows a b equals 0, 0, and 0, 1, and column cd equals 0, 0, and 0, 1. Cells M0, M1, M2, M5, M6, M7, M8, and M9. This group eliminates variables c and d because they vary, and leaves a prime, since rows 0, 0, and 0, 1 both have a equals 0, and b prime, since rows 0, 0, and 0, 1 both have b equals 0. The term is a prime dot b prime. Another group of 4 cells covering M10, M14, M11, M15 if also don't care can give the term c dot d, etc. By repeatedly picking the largest non-overlapping groups, we end with the minimal sum of products. F equals a prime dot b prime plus c dot d example. The key strategy is always to start with groups of 16, then 8, then 4, then 2, then 1, using don't care cells to enlarge groups whenever possible. Don't care conditions marked X are minterms where the output can be chosen as 0 or 1, without affecting the overall circuit function. They are useful for creating larger groups. Example: f of a, b, c, d equals sigma m of 1, 3, 7, 11. D of a, b, c, d equals sigma m of 0, 2, 8, 10. Fill the map with ones for the listed minterms and x's for don't cares. By treating x's as ones, we can form a group of 8 cells covering the entire first column, c equals 0, d equals 0, which includes minterms 0, 1, 2, 3, 8, 9, 10, 11. This yields the term c prime d prime. The remaining one at M7 can be grouped with x at M6 to form a pair, giving term a by c. The minimal SOP becomes f equals c prime d prime plus a by c. If we had not used the don't care cells, more and smaller groups would be required, leading to a longer expression. Product of sums POS, minimization works with zeros max terms instead of ones. In a 4-variable map, we place zeros where the function is false and treat ones, including don't cares if allowed, as don't care for grouping zeros. Example: f of a, b, c, d equals product of max terms 0, 1, 2, 5, 6, 7, 8, 9, 10, 14. It is the same as the sum of products example but expressed with max terms. Plot zeros in those cells, the rest are ones or XS. Group the zeros in the largest possible rectangles. Suppose we can group a block of 4 zeros covering rows a b equals 0, 1 and column cd equals 0, 0, 0, 1, cells M4, M5, M6, M7. This block eliminates c and d, leaving the sum term a plus b prime. Similarly, a block of 8 zeros covering rows a b equals 1, 0 and 1, 1, all columns, yields a prime plus b. The final minimal product of sums is f equals a plus b prime and a prime plus b. This expression uses fewer literals than the canonical product of sums and is derived entirely by grouping zeros on the K-map. A typical exam problem might read: simplify the Boolean function f of a, b, c is sigma m of 1, 2, 4, 5, 6, 7. D of a bc is sigma m of 0, 3. Step 1. Draw a 3-variable K-map with rows a b equals 0, 0, 0, 1, 1, 1, 1, 0 and column c equals 0, 1. Step 2. Place ones in cells 1, 2, 4, 5, 6, 7 and x's in cells 0 and 3. Step 3. Form the largest groups using x's when helpful. We can group a block of 4 ones covering cells 4, 5, 6, 7, row a b equals 0, 1 and 1, 1. Column c equals 1, giving term b and c. Another group of 4 can be formed by using the x at 0 together with 1, 2, 3 to make a column group for c prime equals 0, resulting in term c prime. The remaining one at cell 2 is already covered, so the minimal sum of products is f equals b and c plus c prime. Step-by-step explanation with the map drawn shows how each grouping eliminates variables, resulting in a compact expression. For 2-variable and 4-variable versions, the same procedure applies. Construct the map, place don't cares, make biggest possible groups, write the product terms, and finally combine them. Common pitfalls. 1. Forgetting gray code order. Adjacent cells must differ by only one variable. Otherwise, groups produce incorrect terms. 2. Ignoring wrap-around. Groups can span the left, right, and top-bottom edges. Missing this loses larger groups. 3. Treating don't care cells as zeros. They should be used as ones for SOP or as zeros for POS to enlarge groups. 4. Not checking for essential prime implicants. You might drop a term that covers a unique minterm, leading to an incomplete expression. 5. Creating overlapping groups that are not power of 2 sized. Only sizes 1, 2, 4, 8, and so on are allowed. Shortcuts. Start grouping from the biggest possible size 16 to 8 to 4 to 2 to 1. Mark each covered minterm to avoid redundant groups, and use a checklist. Gray code, wrap around, don't care usage, essential implicants. Remember the cheat sheet of minterm numbers for each map size. This speeds up locating cells during exams.